All right, we're starting with 4.6 notes today on related rates. These are all going to be word problems. How exciting. Okay, so first slide. For beginning, I guess it's important to recognize that, the hardest part is usually pulling from the equation, pulling from the word problem an equation that we can take the derivative of. Doing some calculus, we need to take the derivative of an equation, so got to start with an equation. You're looking for an equation that will relate the variable that you're looking for with some other rate that we know of that's given in the problem. So just takes a little practice to come up with the equation. When you're taking the derivative of your equation, you're always going to be taking it with respect to time, and it's quite possible that you're going to have to do that implicitly, meaning that your variables might be on the same side of the equation. So be careful taking the derivative. Remember what we practiced in chapter 3. And also when you're taking the derivative, it's always going to be with respect to time. So that means that when you're doing this implicit differentiation, you'll have dt on the bottom of every rate. That's what makes it a rate. It's with respect to time. It's probably a good idea if we just go ahead and get started with the examples. So for starters, I picked a problem having to do with the area of a triangle. And hopefully you might recall from geometry, you had this formula for the area of a triangle. And rather than always using 1/2 base times height, it was kind of nice to have the area of a triangle in terms of two sides, as long as you knew the angle between them. So again, our triangle, something like that. If I know this side and I know this side and I know this angle, that's the included angle between them, I can come up with the area of the triangle. All right, so I started off with the area formula and I took its derivative, and because all these letters are variables and they're all on the same side of the equation, I have to do it implicitly when I take the derivative. Also, there's 3 variables over there, so I want to do a product rule, but I've got 3 things in my product, so I'm going to actually pretend like there's only 2 things in my product. So A is my first part of the product, and the second part of my product is going to be b sine theta. So when I'm looking down here, this is my product rule, and inside of my product rule I have another product. B sine theta is going to be another product. All right, so the 1/2 stays out in front. I have my first thing, which is just a, and I take the derivative of the red part that I underlined. So the derivative of the red part is a product rule in itself. So I have the first thing b, derivative of sine is cosine theta d theta dt, and derivative of sine, or excuse me, plus the second thing, sine theta, times derivative of the first thing, bt db dt. All right, and then the big product rule picture again, we did the first, derivative of second, so plus the second is the red part, b sine theta, times the derivative of the first is db dt. From there, I just distribute the a to get that final answer there. Okay, so kind of just more of a review on implicit differentiation than anything there. Okay, second example. Kind of wondering where my sidebar went. It's okay, we'll just go with it. Okay, so we have a trough, and I drew the picture, and it's 15 feet long, 4 feet across the top, and 3 feet for its height. So it tells us water is going to be running into the trough at a rate of 2.5 feet cubed per minute. So the units are really helpful here in trying to identify what exactly that is. So feet cubed would be a unit of volume, and they say per time, so that means they're giving us a rate. So this is actually going to be what we have as dV dt. Okay. The other given information is at the very end. It says, how fast is the water level rising when it is 2 feet deep? Okay, so the 2 feet deep is going to be basically at a certain moment in time, our height is 2. Again, looking at the units can be useful. It's feet. It's not per unit of time. It's not a rate. So this is just a exact moment in time when the height happens to be 2. So the water level is filling the object, filling our trough from bottom up, And at the point when the height of the water is 2 feet, the question is, how fast is the water level rising? So again, I'll underline how fast is the water level rising. So if our water level is what we've been calling H here, then the question is asking us for a rate, dH. How do I make that go away? Go away. Okay, sorry, bear with me here. Okay, so our rate, dH dt. Okay, that's our question. That's equal question mark. A little messy. I'm working with the pen here. Okay, so let's go ahead and get started with the solution. So by similar triangles, I can set up a proportion, and up here, if I call just this distance across is going to be my x, and the vertical distance here is what we were calling h, then I have x's to h as 2:3. Now the 2 and 3, come up here, change colors. So going across, this is 2. I believe the original dimension was 4 all the way across. So it's 2 and 2. And the 3 is going to be the height all the way down here is 3. So I have 2:3 as x is to h. So I got x by itself, and I have a relationship between x and h. If I were to take the derivative of this equation, I could take the derivative with respect to time. I'd get dx dt, and I'd have that equal to 2/3 of dh dt. And that is a valid equation that we could use if we felt like doing it that way. I actually started thinking of it with volume. So the question was to find dH dt, and they gave me dV dt, so I figured, oh, well, my volume equation relates V and H. And if I change, the area, the volume of this trough is always the area of the base times however long the trough is. This is a pyramid, so base area times height. So the base area, I then stopped and over here figured out what the area of this base is. So it would be 1/2 base area, 1/2 the base times the height, because it's just a triangle, where the base is 2x and the height is h. And this is going to be basically the area of the portion that has water in it. So it just simplifies to xh. So the volume of water is going to be the base area times the height, where the base area is xh and the height is 15. So I still have too many variables in there for my taste. I could take the derivative right now and do it implicitly with x and h, but I actually made the decision to get rid of x just so that I could have only one variable before I took the derivative. So I came over here with my similar triangles that I started with, and I said x was 2/3 of h. And so if I take that and plug in for x, 2/3 h, I can rewrite my volume equation just in terms of h. So I kind of got out of having to do it implicitly by substituting in before taking the derivative. So anyway, I get, when I simplify, it comes out 10h squared. And then I go ahead and take the derivative of this volume equation. So on the left I had volume, so now I have dV dt. And on the right, my derivative just with power rule, 20h dH dt. And then I'm ready to plug in what they gave me. So dV dt was 2.5, and h was 2. And I can solve and I can get dH dt that way. Just divide through by 40. Simplify a little and I got my answer. Okay, so that's pretty much the main idea there. I have a practice problem, and I would suggest you pause here and work it out, and then hit play, and you'll see the next slide is the answer. So go ahead and pause here. Okay, hopefully you've worked it out. If I go on to the next slide, this will be my answer. So the final answer should have been -3. Hopefully you got that. But the initial question, if I flip backwards here, it was saying that we have a man who's 6 feet tall, and he walks at a rate of 5 feet per second toward the street light that's 16 feet above the ground. And find the rate that the length of his shadow is changing when he's 10 feet from the base of the light. Okay, so I drew my picture, and 16 for the light post, 6 for the light for the height of the man, and I labeled these each separately, X and Y. So we're given that he's walking toward the lamp post 5 feet per second. I called it -5 because the length of X is shrinking. Now, as he's walking toward the lamppost, the length of X is shrinking, and the length of his shadow would be increasing. So the question is find dy dt. I'm expecting that, or I'm sorry, actually the length of y should be shrinking as well. So I'm expecting dy dt to also be a negative when I get my answer. So I set up a proportion using my similar triangles. So height to height, length to length, okay? And I cross multiplied just to make sure I don't have a fraction. And now I went ahead and took the derivative. So in green here, this is what my derivative came out. So again, I'm taking it with respect to time. So the derivative of y is dy dt, the derivative of x is dx dt, and so forth. And at that point, then I go ahead and plug in anything that I know, which is dx dt being -5. So I showed that in red. At that point, the only unknown is dy dt, so I move them to the same side of the equation and solve, and I get my answer. So dy dt is -3 feet per second. So that's the end. I hope it's making sense to you. Thank you very much for doing your homework. See if I can stop my video here. I will see you tomorrow.